Hello everyone, I am Suvrat and today we'll be discussing AtCoder Regular Contest 214. So let's start with the discussion. So the first problem A is same sum grid path is there is an n into n grid. Let I, j denote the cell at the ith row from the top and jth column from the left. You are given n into n characters s11 till snn. Each character is a digit 0 to 9 or question mark. Determine if it is possible to replace each question mark with a digit to satisfy the following condition, and if possible output one such way of replacement. For each I, j from 1 till n, write s I, j as an integer in cell I, j. For a path from cell 1, to cell n, by repeating moves only to adjacent cells to the right or down, let the score of the path be the sum of the integers written in the cells on the path, including the start and end points. Then for all 2n minus 2, cn minus 1 possible paths, the scores are all equal. And the constraints for this problem are n is given from 2 till 100, so the expected time complexity might be O of n cube, because that would be 10 to the power 6 operations. So problem A. In this problem we are given an n cross n grid where the I, j cell belongs to either an integer from 0 to 9 or a question mark, and we need to find, and basically what we can do is we can replace the question mark with any digit from 0 to 9, and what we need to do in this question is find a possible whatever that exact term is, possible way of replacement such that all the paths leading to a cell from 1, while only moving down/right should have the same sum. Same path sum, or to be precise. So, or report impossible. So basically, let's see the test cases. Also, the constraints given are n less than equal to 100. So that means the expected time complexity would be O of n cube. So let's see the test cases. The first test case is 101, 0 question mark 1 question mark. So 101, 0 question mark 1 question mark. So basically, let's give them indexes. So this would be the starting point, and what we need to make sure is that we find a replacement for each of the question marks such that reaching any cell from starting from this cell would be requiring the same path sum no matter what path we take. So So starting from this cell only, if we try to reach this cell only, the path sum required will be 1. And then we can see that if we try to reach this cell using this path, the path sum would be 1 plus 0. Here the path sum would become 1 plus 0 plus 1 if we follow this path. Similarly, here the path sum will become 1 plus 0. Here it will become 1 plus 0 plus 1. So this is 1, this is 2, this is 1, this is 2. So now let's take this square. Let's take this square and try to see what's going on. So in order to reach this cell, we require a sum of 1. In order to reach this cell, we require a sum of 2. And we currently don't have the values for these cells. So then let's just assume these variables x and y. So if these are the variables x and y, then, and we know that we need to reach this cell. To reach this cell, we have a path sum of 1, and to reach this cell, we have a path sum of 2. So to reach this cell, we will have a path sum of 1 plus x when we follow this path. So basically 1 plus x. And now to reach this cell, we have two paths. Either we can take this or we can take this. So if we take this, it will be 2 plus y. If we take this, it will be 1 plus x plus y. So basically 1 plus x plus y must be equal to 2 plus y in order for answer to exist, because no matter what path we take to reach this cell, the total path sum must always be the same, right? So 1 plus x plus y must be equal to 2 plus y. So we can cancel out the y. So basically this cell's own cost doesn't really matter because it would be added in any path we take. So that's why y is cancelled out. And the next we can see comes out to be 1. So we can basically say that this cell has the value 1. So this cell has the value 1. And now we can, let's say that we give this value a, b and c, and we now know that to reach this cell we already had the value 2, to reach this cell we already had the value 2. Now we can also see that to reach this cell, either we can come from here or we can come from here, both will result in the value 2. So again we can just write down 2 here. Now we can see that if we come from this cell to this cell, here we'll have a value of 2 plus a. If we come from here, we'll again have a value of 2 plus a. So this will have a value of 2 plus a. And if we come from here, this cell will have a value of 2 plus b. If we come from here, this cell will also have a value of 2 plus b. So this cell will have a value of 2 plus b. And now if we come from here, this cell will have a value of 2 plus a plus c. Or if we come from here, this cell will have a value of 2 plus a plus b. And since both of these values must be same for each path to have a same path sum, 2 plus a plus c must be equal to 2 plus a plus b. And that must mean that c must be equal to b. Wait, this is 2 plus a plus c, this is 2 plus b plus c, my bad. This would be 2 plus b plus c because this is 2 plus b, right? So this will be 2 plus a plus c is equal to 2 plus b plus c, and 2 and c will get crossed out. So a must be equal to b. So basically these two must be equal, and this can be anything, so that are the only constraints. So we can literally take any value here. So basically one observation we can make from this last case that we solved for this particular triangle, when we found out the values for these two paths, and then from these two found out the values from these two paths. So what do we do is, let's try to generalize this case and see what happens. So let's say that we have a square like this, and let's say in order to reach this cell anywhere from here or here, the total cost was A. Actually, let me write it like this: A, and the cost of this particular cell is small a, this particular cell is small b, this particular cell is small c, this particular cell is small d. So basically, let's say that actually it would be more appropriate if I write a plus a, but let's just say that let's actually do it like this. So in order to arrive at this, after arriving at this cell from either this path or this path, we are given that we always have this sum A. So basically, in the final answer, when we try to arrive at this cell, we will always have this path sum as equal to A. Now what we have is, we now have two different paths that we couldn't take from here. So if we take this path, we will arrive at this cell, and this cell will have the cost of A plus B. And if we take this path, we will arrive at this cell, and this cell will have a total cost of A plus C. And now we have two paths to arrive at this cell, and this path will give us a cost of A plus B plus D, and this path will give us a cost of A plus C plus D. And since both of them must be equal, so A plus B plus D must be equal to A plus C plus D, and A and D will get cancelled out, and B must be equal to C. So basically, we can point out this observation. So this is that in a rectangle like this, these two values must be equal. So if this is A, this is B, A must be equal to B. Now let me write this as an observation, just a second. So let's generalize it. Actually, let's just name this I comma j. So this will be I comma j plus 1, this will be I plus 1 comma j, this will be I plus 1 comma j plus 1. So basically, we just now observed that in a square like this, I comma j plus 1 must be equal to I plus 1 comma j. So this is our observation. So basically, now let's just take some general square and see what happens if we use this observation. Okay. So basically, according to our observation, these two anti-diagonal elements must be equal. So basically, if we take this particular 2 by 2 square, so then these two elements must be same. And if we take this particular 2 by 2 square, these two must be same, and similarly these two must be same. Similarly, we can see that these two and these two must be same. So basically, all the anti-diagonal elements must be the same. So this is one condition that we found out, but we don't know yet that if this condition is sufficient or not. So now we need to check whether if in a grid all the anti-diagonal elements are same, do we still get different path sum values? So basically, let's start at this cell. So obviously, in the first move, I can either be here or I can either be here, and so basically whatever path sum was here will be the same here, because in the first cell the value was A, let me just say A11, and here it was, let's just give this ABB. and C and D. So basically in this cell my path sum was A, and now if I arrive at this cell or I arrive at this cell, on both the cells my path sum would be A plus B only. And now from here I can either go here, here, here or here, and no matter which direction I choose, my path sum would be A plus B plus C only. Here will be A plus B plus C, A plus B plus C, A plus B plus C. And similarly if we do this, again all the cells will have the path sum of A plus B plus C plus D. So basically we can observe here is that in each move we will move down one anti-diagonal line. So basically in the first move we were here, in the second move we were on these cells, in the third move we can be on these cells, in the fourth move we can be on these cells, in the fifth move we can be on these cells, and basically our total sum would be the cost of this cell plus whatever the cost was on this anti-diagonal line plus whatever the cost was on this anti-diagonal line plus whatever. So that's why no matter what path we take for all the cells on an anti-diagonal, let me write that, no matter what path we take for all the cells on an anti-diagonal. So anti-diagonal is nothing but this is a typical diameter, right? So this is what I'm calling an anti-diameter. So no matter what path we take for all the cells on an anti-diagonal, the total path sum is the same. So basically if the total path sum on all these cells are the same, we can say that the total path sum achieved by any path to arrive at this cell would also be the same, because let's say that we need to arrive at this cell, let's say. So what we can do is we can take any path like this, right? So what we can observe is first we had this value, second we had this value, third we had this value, fourth, fifth, sixth. Basically we had one value on each anti-diagonal, and since because of our observation all these values are equal, so no matter what path we take, so here in this path each anti-diagonal value was used once, right? If we try to take some other path, if we take this path, again each anti-diagonal was used once. So no matter what path we take, each anti-diagonal will be used once, and since all the anti-diagonals have the same value, the sum would be the same. Path sum would be the same. So basically because of this we proved that our observation was a sufficient condition. And since it is also necessary, so this will be our solution. Let's just see the next test case before moving on. So this is the next test case, 2026. Let me make a 4x4 matrix. So 2026 question mark 2 question mark 8. Let me just leave out the boxes as empty. Question mark 2 question mark 8 and 2 1 4. So let's start by applying our property. So this diagonal must have this anti-diagonal must have same values. This must be 0 and this must be a 2. These must be 6 6 6 and then this must be 1. But we arrive at a problem in this anti-diagonal because we already have two values which are fixed and which are different. So no matter what value we place here, all values on this anti-diagonal would not be same. So that's why the answer for this test case is -1. So basically we also found out the condition for impossible in this test case. If sum anti-diagonal already has two or more different values, then the answer is -1. So now this solves our question completely, and there can be a lot of ways to implement this, but I'll tell you guys a nice way to actually separate out all the elements on the same anti-diagonal. So let's just take some grid 1 2 3 4 5 6 1 2 3 4 5 6. Okay, so let's do the indexing 1 2 3 4 5 6 1 2 3 4 5 6. So we can see that on this, basically we have an axis like this, right? Sorry, not like this, basically like this. Let's just assume that this is our x-axis, this is our y-axis, and we are trying to write the equation for this line, for a line like this. So for a line like this, if we just rotate this and visualize it, it will look something like this, x, y, and this line. So basically the equation of this line would be, and since it is a 45-degree slope line, because it is basically symmetric, so 45-degree slope line, so this will be of the form x plus y is equal to constant. But obviously this was not necessary to observe this. We could have just simply done this. So basically whenever we move right or down, so if we move here, we will be increasing this index, or if we move here, we will be increasing this index. Similarly, from this, if we move here, we will be increasing this index. If we move here, we will be increasing this index. Here I will increase this index. Here will increase this index. So we have an increase of 1 on the next anti-diagonal. So basically, on this cell, the sum was 1 plus 1 2. On these cells, the sum would be 2 plus 1 3, 2 plus 1 3. Sum is basically, I am talking about I plus j values of each cell. On this cell, the I plus j would be 4, I plus j would be 4, I plus j would be 4, 5, 5, 5, 5, 6, 6, 6, 6, 6, like that. So basically, what we can say that is all cells having the same value of I plus j must have the same digit on them. So basically what we can do is we can make a map of LL comma set, and in this map we can simply store the different values. So map of I comma j, map of I plus j, sorry, let's just say that map of x will store all different values on cells where I plus j is equal to x. So that's how we can store all the different values, and then we can check whether all the values are, check whether there are two or more than two different values on any anti-diagonal or not. And if there are not more than two different values, then we can either, if we already have one value, then we can just use that value for all the anti-diagonal cells, and then if we don't have any single value, then we can just put any number according to us. It's our choice. So the overall time complexity would be O of n log n, sorry, n square log n square actually. So this is simply O of n square log n. So that will be well within the time limit because the maximum time complexity of O of n cube. So let me show you guys the code. So first I take input the array, the grid, n cross n grid. So for that I take input each character, and then if I check whether the character is a question mark or not, if the character is not a question mark, then I simply get its decimal value and put that in ARR of I comma j. Else I just set ARR of I comma j as -1. So basically -1 denotes as not yet initialized, or basically -1 denotes that cell has a question mark in it, on it. And then I'll create the set of different values for all the different possible I plus j sums. So for that what I'll do is run 2 for loops, and then in m of I plus j I'll insert the value of ARR I comma j. So, and since I'll be doing this for all the cells, this map will contain information about all the different cells in the grid. And then I'll maintain a check variable which will tell me if answer is possible or not. And then MP, in this MP I'll just store what the final values for each anti-diagonal will look like. So I'll just iterate over this previous map that we created here, and for each value and each set corresponding to the value. So from the set what I'll do is I'll erase -1 because -1 means not in a -1 means a question mark essentially. And then I'll check that if the size of that set is already greater than 1, then simply my answer is false because that particular anti-diagonal already has 2 or more than 2 different values. And then I'll check if v dot size is equal to 1. So if it is 1, then I can set the MP of val as star v dot begin. So since it has only one value, then I can basically put that value for this anti-diagonal. And if there weren't any values, so that means that all the values on that anti-diagonal were just question marks. So for those anti-diagonals I am just using the value 0, but you can use any value from 0 to 9, you can use any value here. And then if in the end check came out to be false, then that means the answer was impossible, so cout -1. Else for each cell I'll just cout the value on that diagonal, on that anti-diagonal. So that would be the solution for this problem. And since we can see that this is an n square loop, again this map will have a size of O of n and log n for x's, and again, and this map will have a size of O of n, sorry, this map will have a size of O of n square. M will have a size of O of n square because we are inserting n square elements, right? So this is n square log n loop, this is also n square log n loop, and this is an n square loop. So overall time complexity is n square log n. So let's move on to the next problem. So the next problem is missing number in graph. So there is a connected simple undirected graph with n vertices and m edges, where the vertices are numbered 1, 2 till n and the edges are numbered 1, 2 till m. Edge I connects vertices ai and bi. Also there are a total of n plus 1 cards, one each with the integers from 0 to n written on them. Snoop performed the following operations in that order. Place one card on each vertex and eat the remaining one card. For each I, write on edge I the bitwise OR of the integers written on the two cards placed on vertices ai and bi. Let this integer be xi. Discard all cards placed on the vertices. Given the information about graph n, m, a1, a2 till am, b1, b2 till bm and x1, x2 till xm, determine the integer written on the card that snook8. If it cannot be uniquely determined, output -1. If it is guaranteed that the given card x can be obtained by the above operations. and the constraints for this problem are t is less than equal to 10 to the power 4, n is less than equal to 2 into 10 to the power 5, m is less than equal to 2 into 10 to the power 5, and ai and bi are obviously less than equal to n, and the graph is a connected simple undirected graph, and the two other constraints we are given are sum of n over all test cases is at most 2e5 and sum of m over all test cases is at most 2e5, and all input values are integers. So basically, because of these two conditions, the expected time complexity would be around O of n or O of m. So So in this problem, we are given a graph of n vertices and m edges, and basically this is an connected undirected graph. So connected means that from each node we can visit every other node. So basically all the nodes are connected by every other node through some edges. It cannot be like this. It cannot have two separate connected components. All the nodes are in a single connected component. And undirected means if the edge is from A to B, it is also from B to A. That is undirected. And in this problem, what we are doing is basically for each node we selected a value from 0 to n we selected a distinct value from 0 to n. And obviously here we have n plus 1 values, right? So there will be one value left over because we need to only select n values from here. We actually selected only n values from here since we have n vertices only. And what we did after selecting the values was that for each edge we give it the value C of AI or C of BI. So basically C of AI is the distinct value that we gave to the node AI, and C of BI is the distinct value that we gave to node BI, and simply there is an edge between the node AI and BI, and on this edge the value of this edge is simply CAI or CBI. And when we give out all the values to all the edges, we actually call this xi. And in this particular problem we are given all the edges AI to BI and xi. So we are given AI, BI and xi, and we need to find which value was not selected. So let's see the test cases now. The first test case is n is equal to 2 and m is equal to 1, so we just have a single edge 1 2 3. So 1 2 2 and we have the value 3, and so basically we have the value 0 1 and 2 that we could have selected these values from, but we can see that the only pair that will give the value 3 for this edge is 1 2. So that must mean that these vertices must have the values 1 2, and because of that the unused value will be 0. So the answer for this test case is 0. So the answer for this test case is 0. Now in the next test case we have 1 vertex and 0 edge. So obviously if we have 1 vertex and 0 edge, then we cannot determine whether this vertex had the value 0 or it had the value 1. So that's why it is impossible to determine which number was unused. So the answer for this test case is -1. Now in this test case we have 2 1 4. So 2 1 has the 4, 1 3 has 5, and then 1 4 has 7, then 2 3 has 1. Let me actually let me erase this as well, and so 1 3 has the value 5 and then 2 3 has the value 1. Okay. So actually let's start this problem with what we can do is we need to find the values, right? So obviously we know a very obvious property of XOR is that if this is a b and the value written in between is a or b, so let's say that the value on this vertex is x and the value on this vertex my bad. So let's say that the value on this vertex is a, small a, the value on this vertex is small b, and the value of the edge that we were given was x. So we know that x is simply equal to a or b. So what happens if we XOR by a on both sides? So a XOR a is simply 0 and 0 XOR b will be b only. So a XOR x is nothing but b, and similarly b XOR x is nothing but a. So what does this mean? That if for either of the vertices we know the value, we can simply XOR it with whatever the value of the edge is and we will get this value. So what I am saying is, let's say that this one has the value x, then this would be simply XOR 5 and this would be simply XOR 5 XOR 1 and this would be simply XOR 7. So whatever value we take for one, according to that we will decide all the other 3 values. So actually what we can see now is if we take the XOR of all these 4 numbers, so basically if we take the XOR of x, XOR XOR 5, XOR XOR 7, XOR XOR 5 XOR 1. So actually here this x and this x will cancel out and this x and this x will cancel out, so this will just become 0 XOR 5 XOR 7 XOR 5 XOR 1. Actually this 0 is not necessary. So 5 XOR 7 XOR 5 XOR 1. So this is some constant value. So for this particular test case, what we got was that XOR of all vertices was a constant value. So if XOR of all vertices is a constant value and we were actually selecting n values from these n plus 1 value and wanted to find out what was the last value remaining. So for that, what we can do is, since zeros or ones or 2 till n, these are the original numbers that we had to choose from. So these are n plus 1 numbers, and if we XOR this with whatever constant this was, then we will basically cancel out all the n numbers that were used, and we will be only left with the number that was unused, because a XOR a is obviously 0. So this constant, it will have XOR of the n numbers that were selected, and these are all the n plus 1 numbers. So this will be equal to the unused number. So actually, let's just try to find. So 5 XOR 7 XOR 5 XOR 1 will be 7 XOR 1, which is 6, and 0 1 2 3 4 5 0 1 2 3 4, sorry, yep. So 0 XOR 1 XOR 2 XOR 3 XOR 4 XOR 6 will be our answer. So 1 XOR 2 is 3, 3 XOR 3 is 0, 0 XOR 4 is 4, 4 XOR 6 is 2. So here we can see that the answer for this particular test case is 2. So actually what we need to focus on was that was this property, XOR of all vertices was a constant value or not. So is this applicable for all the test cases? Because if this is applicable for all the test cases, we will be able to find the answer for all the test cases, right? So let's just make some graph here. So a graph will somewhat look like this, right? It might have some cycles, well, just like this. So if we mark some node as the root, so and assign it the value x, this will be x or some constant. So let's just denote that constant as currently a1. This will be XOR a2, this will be XOR a3, and similarly XOR a4, similarly XOR a5, XOR a6, XOR a7, XOR a8, XOR a9, and XOR a. Okay, wait, did I 1 2 3 4 5 6 7 8 9? Yep, that's fine. So what we see is that when we take XOR of all the nodes, this x and this x will cancel each other out, this x and this x will cancel each other out, this x, this x, this x, this x, this x, and this x. So all the x will cancel each other out. So what will be remaining with is a constant value. So why did all the x cancel each other out? Because the number of nodes were even. So what we can say is that if the number of nodes are even, XOR of all the vertices value does not depend on x. So what we can do is we can simply take x is equal to 0 and just calculate all of these. So how will we calculate all of these? Obviously from this node we will calculate the value for this node, this node, this node, and then using these three nodes we will calculate for this node and this node and this node. Then again we can just keep on going like this. So from the parent node we will calculate the value for the child node, because we saw that if this has the value a and this has the value x, this will have the value a or x. We already saw that. So since if we know this value and we know what the edge has the value, we will get to know this value as well. So using just this we will be able to find the values of all the nodes if we just take x is equal to 0, and we already proved that if the number of nodes are even, XOR of all the vertices value does not depend on x. And once we find that constant value, we can just XOR it with 1 XOR, 2 XOR, 3 XOR till n, and this will be our answer. So this is the case where n is even, right? But what happens when n is odd? So let's talk about that. For when n is odd, then obviously since n is odd, all the x will not cancel each other out. So basically the value of x will not get, so actually the XOR of all vertices will still depend on x. And actually if you see that this a1, a2, a3, a4 actually does not depend on what the x is. So we saw that here, right? Here it was x. So no matter what x was, a1 would always be 5 because a1 only depends on this edge values. a1, a2, a3, a4 only depend on the edge values. So this is XOR 5, this is XOR 5, XOR 1, this is XOR 7. So it only depends on the edge values. So this will be a constant, right? This will be a constant. So for an odd XOR of all vertices, so the XOR of all vertices will look something like x XOR some constant, x XOR the constant. And if we do x XOR the constant XORed by 1 XOR, 2 XOR till n, so now it will become something x XORed something. And now obviously x can be anything from 0 to n. Actually not anything from 0 to n, because obviously x cannot be something that that makes one of the values of these nodes greater than 1, actually greater than n, because obviously that would be a violation. But there must be one x satisfying this equation, right? We know that there must be one x satisfying the equation, because then only we got this tree in the first place, then only we got these edges value in the first place. So one x must satisfy, right? But what we can say in the case of odd vertices, odd number of vertices, x XORed 1 will also satisfy. So let's say that let me write this actually more precisely. So if x bar is a solution, is a valid value of x, then x bar XOR 1 will also be valid, because what this XOR 1 will do is it will just add on to each node. So this node will become XOR 1, this node will become XOR 1, this node will become, every node will become XOR 1, because it is propagating, right? The value of x just became XOR 1 for each x. So these all become XOR 1. And XOR 1, so x XOR 1 is, we can point out this property that a XOR 1 is equal to either a plus 1 or a minus 1. Or actually, to be more precise, a XOR 1 is equal to a plus 1 if a is even, and a minus 1, actually if the last bit is 0, that means that the a is even. So yep, and a minus 1 if a is odd. So a plus 1 if a is even, and obviously we are given that in the problem n is odd, right? N is odd. So n minus 1 will be even and n will be odd, right? So after if x bar is a valid solution, then x bar XOR 1 will also be valid, because what XOR1 will do is change each vertice's value according to this rule, and we can say that after applying and we can say that if we use this value, even when we use this value, no vertice will have a value of greater than n. So for x bar XOR1 also, no vertice will have value greater than n. So x bar XOR1 will also be a valid x, because n is odd, right? So this will transform to n minus 1 and n minus 1 will transform to n plus 1, and all the numbers before that we don't even have to worry. So we can see that this is n. So we can see that no number actually crosses n. Each and every vertex will have a value less than equal to n. So x bar XOR1 is also valid. So basically for this problem we'll have a minimum of two solutions. One will be this, the second will be x bar constant XOR constant XOR 1 2 till n XOR 1. So this one will make the number, or will change the number. Basically it will change the odd number to even and even number to odd. So basically we'll have two different solutions. Hence for this case the answer will be minus 1. So when n is odd, answer is minus 1, and when n is even, just take value of node 1 as 0 and find all other values, and the answer is simply 1 XOR 2 XOR 3 till n XORed by C1 XOR C2 till Cn. So C1, C2, Cn is the value of each node. So this can be easily implemented by using a DFS in O of n, and I'll show you guys the code for that now. So I have declared my graph as a global vector of pair. So in each pair I'll store the edge vertex and the weight of the edge. So first of all, for each n I'll just clear out the previously stored values in the graph and also reset the visited array, and then I'll set my answer to 0, which you guys will understand in a moment. And for all the edges I'll store them like this. G dot A would be connected to B with a weight of x, and B would be connected to A with a weight of x. And if n is odd, then I'll simply see out minus 1 and continue. Else so this all is nothing but the XOR of 1 till n. So this value, basically this value, and now I am calculating this value using a DFS. So what I am doing is DFS I'll call from the node 1 and start with a value of 0, and what this DFS will do is it will go to the child and update the value to whatever it was XORed by the edge that it traveled. So the next node is child and the weight of edge is val, and the DFS will go on to the child node with the new value of whatever the current value was XORed by the edge it traveled. And also, since the value of this node is cur XOR val, so I'll also do answer XOR equal to val. Or what I could have done is I have written just before this viz on this line that answer XOR equal to cur. That would also give us the right answer, because cur is nothing but the current XOR value for current value of our node, and when we XOR the current value with the edge value, we get the value for the next node that we are going to. So this simple DFS will update the value of answer variable to be the XOR of all nodes, and in the end we can just do all XOR answer, and that is it. So, and obviously this DFS is O of n, since it visits each node exactly once. So that was the solution for problem B. Let's move on to problem C. So problem C is there are n people numbered 1 2 till n. The strength of person I is pi, and each person I is assigned to one of the teams A, B, C, D to form 4 teams. There are 4 to the power n ways to form teams. Among these, find the number modulo 998244353 of formations that satisfy all of the following conditions. Each of the teams A, B, C, D has at least one person. The sum of strengths of the people in team A equal to the sum of strengths of the people in team B. Sum of strengths of people in team C equal to sum of strengths of people in team D. And the constraints for this problem are n is less than equal to 500 and p is less than equal to 1e5. Actually, sum of all p is less than equal to 1e5. So expected time complexity would be around n into sum of all p. So n into sum of all p would be 500 into 10 to the power 5, which is 5 into 10 to the power 7, which would pass. So that would be the expected complexity. And obviously the first thought when we see constraints like this is that the question might be requiring some dynamic programming, because only in dynamic programming solutions are the constraints this tight, and obviously n500 and summation p less than equal to 10 to the power 5 gives us the hint that one of the state is n and the other state is somewhat sum. So that is a hint. So let's see the problem. So in problem C, we have P I as the strength of person I, and we need to actually make 4 teams A, B, C, D, such that each player will go into exactly one team. Each person actually in exactly one team. So each player will have a choice to go to 4 different teams, right? And since there are total of n players, so total number of team formations would be 4 into 4 into 4 n times, which is 4 to the power n. So that's why it is written there are 4 to the power n ways to form teams. Now what we need to do is count number of formations which satisfy that sum of all players in team A is equal to sum of all players in team B, actually sum of all strength of all players, and sum of strength of players in team C is equal to sum of strength of players in team D. And no team is empty. Actually, more formally, each team has greater than equal to one person or player, whatever. So let's see the first test case, 1 1 2 2. So n equal to 4 1 1 2 2. So we can obviously see that it must be divided like this. The first team must have 1 and the second team must have 1, and then third and fourth C and D team must have 2 2. Only then A will have the sum 1, B will have the sum 1, C will have the sum 2, and D will have the sum 2. Now A, B, C, D. So let's name this as the person 1, person 2, person 3, person 4. So this can be either 1 2 3 4, or it can be 1 2 4 3, or it can be 2 1 3 4, or it can be 2 1 4 3, and this will be one arrangement. The other arrangement can be 2 2 1 1, A B C D. So again similarly we will have 3 4 1 2, 4 3 1 2. Now again oh my bad, actually okay, let's just do it like this: 3 4 2 1 and 4 3 2 1. So these will be the 8 different possible arrangements that result in A, B, C and D teams being the same. So the answer for this test case is 8. So actually test case will not help much in this problem. We can obviously see that there are no particular observations that we can make in this problem, and we already know that a similar problem is that number of ways to divide a set in two parts such that each has the same sum. So this is a well-known dynamic programming problem, but obviously we don't have this problem currently with us. We have that team A and team B and must have the same sum, and team C and team D must have the same sum. If the problem had been that we need to only divide in team A and B such that the sum of A is equal to sum of B, and we need to count the number of ways to do this, then we would be using this exact solution of DP. But our current problem is a little more complex problem than this. So obviously if this requires DP, then our current problem will also require DP only, and the constraints also suggest that. So first of all, before moving on to this current problem, let's see how can we solve this problem. So most of you, if you regularly attempt AtCoder regulars and are able to solve problem C or come close to solving problem C, must already know this solution pretty. This is a pretty well-known problem. So how do we solve this? So this has a solution with this corresponding state. So dp I comma sum. So this state stores the value that number of ways I can get sum from players I plus 1 till n. So actually also this is very similar, very similar to knapsack, almost similar to knapsack. So the dp I comma sum will store the number of ways I can get sum from players I plus 1 till n. Sum is basically that I need to select some set of players that have the summation equal to sum. Actually, let me just try it. That is fine, I guess. So obviously we have two different possible choices here. We can either take the ith player, or we cannot take the, or we don't take the ith player. So if we take the ith player, this will become I plus 1 plus sum minus whatever the value of I was, plus the number of ways when we don't take the ith player, that would be dp of I plus 1 comma sum. Here sum will remain the same because we are not taking the ith player, else here sum will decrease by vi because we are taking the ith player. So if we add these two, we will be covering all the different possibilities, and this will give us the answer. So now if we need to calculate the number of ways where two sets have the same sum, then obviously if two sets have the same sum, they will have the sum of total upon 2, right? Whatever the total sum is by 2 will be the sum of each set. So that would be simply dp of 0 comma total by 2. and obviously total must be even. So dp of 0 comma total by 2 will tell the different choices that we can make starting from the 0th player to achieve a sum of total by 2, and that would be the total different number of ways. So now since we know this problem, let's continue focusing on to the current problem. So our current problem involves that for each player, also let's just, instead of looking at these conditions like this, let's look at this condition, these conditions like this. Sum of a minus sum of b is equal to 0, and sum of c minus sum of d is equal to 0, right? And we can actually rewrite this to be sum of a plus sum of minus b and sum of c plus sum of minus d to be equal to 0. So basically what we are doing here is that for each player we have 4 different choices to make. We can either put it in team A, or we can put it in team B, or we can put it in team C, or we can put it in team D. And we know that if we put in the total players, that the total sum that we put in team A must be equal to total sum that we put in team B. So actually team B will reduce this equation by whatever the value I am using, and team A will increase the value in this equation, right? If we look at this particular equation, if I select some player to go into this team, then the value of this will increase, and if I select to go in this team, then the value of this will decrease. So actually what we can do is we can use something known as the multinomial theorem. Everyone must have studied this in the chapter binomial theorem during your class 11-12th. So how will we use this multinomial theorem is that we will quantify this problem to a problem like this. So basically what we'll do is we will have 4 choices: x to the power pi, or we'll have x to the power minus pi, or we'll have y to the power pi, or we'll have y to the power minus pi. So actually these will be the 4 different choices that we can make. So if we make this choice, then that means I'm going into team A. If we make this choice, then that means I'm going into team B. If we make this choice, then that means I'm going into team C, team D. Minus, because this will reduce the power of y, this will increase the power of y, this will reduce the power of p, this will increase the power of p. So basically if we look at all the terms that will come in expansion of this, we will see that each term will be a multiplication of one of the terms from each of the brackets. So basically if we have 3 brackets like this, we will have to select one term from each of the, actually let's make it 4, we will have to select one term from each of the 4 brackets, and that one term will be corresponding to which team we select, and in the end we are given that the sum of A sum of A minus sum of B must be 0, right? So the total power of x must be 0 and total power of y must be 0. So our problem actually comes down to coefficient of x to the power 0, y to the power 0 in expansion of this. So if we try to further simplify this, because obviously this is a quite difficult problem to solve in 2 variables, so let's use some kind of trick. So let's look at this like this. So this will be x of pi plus y of pi into 1 plus xy to the power minus pi. So when we open this bracket, this obviously is x of pi plus y of pi, and then this into this is y of minus pi, and this into this is x of minus pi. So we can actually write these four terms as this, like this. And we can now write this like this: pi of x of pi plus y of pi into 1 plus xy of minus pi. Actually, I meant to do this, sorry. Okay, let's move a little bit further. Pi of this and this. So what we can do is basically separate out these two pi's. So now obviously let's say that S is the total sum of pi, right? We can just use this as a variable so that we don't need to write sigma pi everywhere. So each and every term in the expansion of just this pi would be looking something like this, right? 1 plus something x y to the power minus some a1 plus xy to the power minus some a2 and so on. Both x and y will have the same power, right? Both x and y will have the same power. And here in the expansion of this, it will be looking something like this: x of whatever r1 and then y of whatever r2. They can be different, but r1 plus r2 must be equal to s. They must be equal to s. And now in this we need to find the coefficient of x to the power 0 and y to the power 0. So basically we need to select terms from this and this bracket that actually multiply with each other to give the power zeros. And since here both x and y have the same power, we need to select terms from here like that only. So we need to select terms where x, y have the same power r1. So basically r1 is equal to r2, and since we know that r1 plus r2 is equal to s, this gives us the value of r1 equal to r2 as s by 2. So basically x1 y1 to the power of s by 2 we will have to select from this bracket, and then obviously because we need x to the power 0 y to the power 0, we will have to select x1 y1 to the power minus s by 2 from this bracket. So we need to, now our problem is simply pi of x of pi plus y of pi in this coefficient of x1 y1 to the power s by 2, and in this 1 plus xy to the power minus pi coefficient of So we need these two terms, these two values, because multiplication of these two values would be the final coefficient of x to the power 0, y to the power 0. So now this, if we look at it closely, this is the initial problem that we discussed, this problem. Number of ways to divide a set in two parts. So we can see that clearly here we have two choices. We can either select x or we can select y, and in the end both of them must have the power s by 2. So basically the summation of all the persons in both the sets must be same. So this is the initial problem, and we can use dp of 0 comma total by 2 to solve this. Now let's look at this, and again this is obviously the same problem. Here we also need to find out how many PIs, find out what PIs we need to select to get the sum minus s by 2, and again that is dp of 0 comma total by 2. So both are essentially, we are just finding out which subsets of pi gives the sum total by 2, or actually what two different subsets we can what number of different subsets we can find that have the total sum as total sum by 2. So basically both the equations will have the same coefficient. So let's just denote the coefficient of this as x, then the coefficient of this will also be x, since both of them are simply number of ways to make sum total by 2. So basically the final coefficient of x to the power 0, y to the power 0 will be x square. But this is not yet our answer. Our answer is basically x square minus 2x. And where will this minus 2x come from? We had one more condition, that no team should be empty. And we have not yet removed those cases. So basically let's just assume that one of the team is empty. So if we say that team A is empty, then team B will also be empty, because sum of team A is equal to sum of team B. So basically this is 0, and sum of C is equal to sum of D. So basically this is essentially just dividing our given set into two different sets of the same sum. So that is again dp of 0 comma total by 2, which is x. And also vice versa, these two could be 0 and these two could be the two teams that have some value. So minus 2x actually, not just x. So x square minus 2x will be the answer, where x is the number of ways to select a set U which has set of persons U which has the sum equal to total sum by 2. And obviously x is 0 when n is odd. We also saw that when total sum is odd, because when total sum is odd, total by 2 will not exist, it will be a decimal value. So x square minus 2x when n is even, and when n is odd, answer is 0. So I'll show you guys the code now. So here I am using this dp. So it is just as I explained in the solution. It is simply the sum of dp I plus 1 comma sum minus vi and dp I plus 1 comma sum. So this is taking the ith person and this is not taking the ith person. And this is just for memoization, this is for memoization, and this is the mod. And in the end the sum must be 0. So if there is some remaining sum, then that is not a valid way, else it is a valid way. So I take C in n, then take the input vector, then I find the total sum and I memset the dp, and if total is odd, then I simply see out 0, else I find this is the x, actually I am denoting it with ct. So this is dp of 0 comma total by 2, and then answer is simply ct into ct minus 2 into ct. So the overall time complexity, we can see that it is n into sum. So that would be 5 into 10 to the power 7, which is good enough, as we discussed earlier. So that was the solution for problem C, and that was it for today's discussion. So thank you guys.